Alright, calculus, here we go, AP sample test number 3. This is actually the second packet because we started on number 2. I know I'm kind of starting us off a little bit weird there. We're going to be doing multiple choice. I'm actually going to do all the non-calculator, not just 1 through 9, but 1 through 28, all the way through there for the multiple choice. So let's go ahead and get started. So we start with this first problem. It says the area of the region between the graph of this and the x-axis from here to here. It's just basically saying the integral of y from 1 to 3 dx. Well, we do have to do it by hand, so let's go ahead and work it out. It's going to be the integral of 3x squared plus 2x from 1 to 3 dx, of course. When we take the integral here, we're going to be using simple power rule. So we add 1 to the power and divide by that. So it's going to be 3x cubed over 3 plus 2x squared over 2. Conveniently, the 2's reduce and the 3's reduce. We're going to be evaluating this from 1 to 3. So that means we have 3 cubed plus 3 squared. That's our top piece, or f of b, minus 1 cubed plus 1 squared. So this is 2 here, and this is 27 plus 9. 27 plus 9 is going to give us 36, minus 2 is 34. It's that easy. Remember, the first one's always pretty straightforward. No extra special stuff going on with it. All you got to do is evaluate. Let's look at number 2. Alright, we have a limit here. The first thing that you do with most any limit is you just plug in and see what happens. So if I have the limit as x approaches 3 minus x squared over x minus 3. If I were to plug in 3, I would have 3 minus 3 up top, and I'd have 3 minus 3 on bottom, and the top one would be squared. Well, with that in mind, I would see that the top is going to go to 0 and the bottom's going to go to 0. That tells me that I need to do some algebra. Do some algebra to reduce first. Because when I reduce, that 0 on top and bottom, it's going to be gone. Somehow I need to factor things and figure out what can pull apart. Well, when I look at this, first I notice that they're very similar. This has a minus b, and on the bottom it's b minus a. Well, the cool thing is, if I multiply the top and bottom by negative 1, then I'd have limit as x approaches 3 of 3 minus x. We're going to multiply this by negative 1. That's 3 minus x squared. We're going to multiply the bottom by negative 1 as well, and that's x minus 3. If I distribute this negative 1 to the bottom pieces, that'll become the limit as x approaches 3. And on top we'll still have negative 1 times 3 minus x quantity squared over, now when I distribute this negative, that's going to become negative x and positive 3. So if I rewrite that with positive 1 first, I'll have 3 minus x. This is actually kind of convenient because now I can reduce. This 3 minus x can reduce with one of the 3 minus x's on top. And we're just going to have a negative 1 times this term here. Now that I've done that, I can plug in the 3. This is going to be negative 1 times 3 minus 3 over 1, which is really just 0, because 3 minus 3 is 0 times negative 1 divided by 1. All of that's still going to be 0. Why is it okay that we do this now? Because there's no more 0 in the denominator. Now we can follow proper math protocol. Let's look at number 3. This one's talking specifically about units. It says, for a car traveling at a speed s miles per hour, the fuel consumption of the car CS is measured in gallons per mile. What are the units of the integral of this? Sometimes it's hard to think back on specifically how units change. So let's take one example and see what the pattern is and then apply it from there. The easiest example I can think of with units is just straightforward velocity. not talking about cost of gallons per mile or consumption of fuel, but just miles per hour. So if we have velocity, that's something that can be written in miles per hour. If we're doing acceleration, that would be miles per hour per hour. And if we do position, if we take the integral of velocity, we're going to actually get just miles. It's a measurement of distance. So we either divide by an hour if we're taking the derivative, or we multiply by an hour to be moving up. So that unit of time, that denominator, reduces in power. So when we see this, RCS is in gallons per mile. So this right here, this is in gallons per mile. So we're going to lose this mile, and we're just going to have gallons. That means our answer would be A. That was pretty easy. The radius of a sphere is increasing at a rate of 2 inches per second. Whoa, hold the phone. I have a measure. And I have the word increasing, or it could have been decreasing, at a rate of 2 inches, a rate of 2 something. Those three ingredients, anytime I see those things, the topic I should be thinking is related rates. Anytime that we're talking about related rates, that means first we need to start with our formula that kind of brings it all together. What should we call that? The general formula, I guess, the general relationship. It includes all variables. Includes all variables. So that's the first thing we're going to do. Then we're going to take the derivative with respect to time implicitly. And then we're going to substitute and solve. I mean, it's pretty much that easy. It's very much a mechanical type of process. So what's the general relationship of the piece that we're talking about here? Well, we're talking about a sphere. Let's draw a sphere, just for fun. Here's a circle. And if we give it kind of a horizontal ring there, we can even give it a vertical ring as well, just to add some dimension to it. So we're talking about the radius of the sphere, which starts in the middle here and goes to the edge. And that radius is growing. It says it's increasing right here at a rate of 2 inches per second. So we're increasing at a rate of 2 inches per second. So let's start interpreting the information that we have right now. It's asking me to find how fast is the volume increasing. So the question is, what does dV dt equal? What's the rate of volume over time? Well, they give me, I'm given, dr dt, which is this piece right here. It's a rate of a radius of a sphere. So dr dt equals 2 inches per second. So I need a formula that relates radius and volume of a sphere. Well, that would be the volume of a sphere. The volume of a sphere is V equals 4/3 pi times the radius cubed. This formula would be given to you. It would be somewhere like in parentheses right here. It would be V equals 4/3 pi r cubed. The volume of a sphere is that. They would tell you that, because they don't want you to forget some geometry formula and have that screw you on a calculus part. Once I have this now, check. I'm going to take the derivative with respect to time implicitly. So I take the derivative all the way across. Well, the derivative of v to the first power is just 1 times dv dt. equals, well, 4/3 pi, that's going to be a constant, so we'll just write that in here, 4/3 pi. And then we're going to take the derivative of the r part of the term. That's going to be 3r squared dr dt. And now I'm going to start substituting the pieces that I have and figure out what I need in the long run. So dv dt times 1, that's still just dv dt, and I'm going to leave that alone on this side because I want that. That's what I want to have solved. I'll isolate it on that side. But I can substitute r. So now I'm going to have 4 times 4 over 3 times pi times 3 times r squared. And this time r is 10. Where did I know that? Right here. The radius is 10 inches. Times dr dt. Well, in this case, dr dt is 2. A whole lot of stuff is going to simplify. First, we have this 3 over 3. That's 1 over 1. 10 squared is really 100. So I have 4 times 100 times 2. That's 800. Don't forget the pi. Now, I do need to realize that this is cubic meters per second. Is it cubic meters? Cubic inches per second. But really over here it doesn't matter. They don't have the units. They're just looking for the value. Particle moves along a straight line so that its velocity is given by here. So automatically they're giving us velocity. It says how far does the particle travel between t equals 1 t equals 3. So it's asking us about distance. Distance equals what given velocity? Well, distance is really the integral of speed from A to B. And speed is really the absolute value of velocity. So this time we're going to take the absolute value of velocity from 1 to 3 dt here. In this case, velocity is t squared, and t squared is greater than 0 when t is between 1 and 3. So then the absolute value of t squared is equal to just t squared. We don't have to make any changes. So then we'll just go from 1 to 3 of t squared dt. We take the antiderivative, t squared becomes t cubed over 3. We're valuing that from 1 to 3. It's going to be 27 over 3 minus 1 over 3. Remember, it's nice to keep these denominators because then you can combine like terms here, or combine fractions. 27 over 3 minus 1 over 3 equals 26/3. Hey, that was way too easy. The derivative of this is, okay, there's a lot of strategies you can apply here. We could try to treat this like a product rule. We could treat it like just one big term and then take the derivative and just do a simple power rule. That's probably what I'm going to do. When I look at this, I see 4 to the 3rd power x to the 3rd power times 2 to the 6th power times x to the 6th power. So I'm going to start with that, and I'm going to take the derivative of this piece. The constants, which I underline here in blue, I'm going to leave those alone. I'm going to combine these two x's together though. So we're really looking at x to the 9th, and then we have 4 to the 3rd, and 2 to the 6th. I'm taking the derivative of that. Well, simple power rule, you leave that what's that piece? That coefficient out front alone. We're going to pull down this 9. So that means we're going to have 9 times x to the 8th. And then out front, we still have those other coefficients, 4 to the 3rd times 2 to the 6th. You might be curious, like, why am I leaving this not multiplied out? Well, this means I have 4 times 4 times 4 times 2 times 2 times 2 times 2 times 2 times 2 times 3 times 3 times x to the 8th. Well, I can almost cancel out some of these. For example, b is gone because this has to be x to the power of 8. I can also see that 72 here, a is gone because 4 times 4 times 4 is 64. And clearly these other parts of the coefficient are going to be bigger than 72. Now as I look at these last three pieces here, I notice one difference in E. This one just has x squared and x to the 5th, which would combine to just become x to the 7th. So that power is too short. So it's just between C and D. And if you look at these, this one has a 2x to the 5th, this one has a 4x squared, so the only difference is this leftover piece here. So let's kind of reduce those pieces out and see what's left over, see how we're going to have these coefficients. Well, the 2x to the 5th, that's 5 2's, and that's going to be 1. Let's start seeing what disappears here. We got 1, 2, 3, 4, 5. And then we got 4x squared, so we're going to take out those two 4's. So what we're really left with is the 2 and the 4 and these two 3's. So that's going to be 8 times 9, which is 72. So it should be D, because the other parts were taken up inside the parentheses there. It's just a little bit of problem solving. There are other ways to do that. To me, that keeps the number small since I don't have a calculator to fall back on. Oh, we gotta erase this. Okay, so let's look at this function. The slope field is shown in the figure above. Which statement is true? If y of 0 is greater than 2, this is a y value, if y is greater than 2. And if we're between 0 is less than y and less than 2. And then if y is less than 0. So we're going to kind of color code this. Actually, let's make these different colors just so we can kind of understand where we're at. So this one is 0 is less than y is less than 2. And then the last one is, let's do green. If 0 is greater than y. So if we're down the bottom. So this would be the green zone. The red zone is in the middle. And the blue zone is on top. So now we can interpret our picture a little bit better. So it's asking, if we have y greater than 2 up in the blue zone, there's going to be a horizontal asymptote. The limit as x approaches infinity of y of x of your function is a horizontal asymptote. So it's saying that there's a horizontal asymptote here at 2. Check. That's true. For the red zone, it's saying if you're between 0 and 2, then as you go off to infinity, so what happens as I go off to infinity in the red zone? Well, let's say I start here and I go up, but then I kind of slow down, and now I have the same horizontal asymptote. So that one's also true. Third one, let's see if we can go 3 for 3. If we're less than 0, then the limit as x approaches infinity is saying that the horizontal asymptote is at 2 again. So say I start here with the green. This one's got a different turn. It actually goes down toward negative infinity. It doesn't have the horizontal asymptote. Now if that were true, this would have actually had to have been negative infinity. The limit as x approaches negative infinity does approximately equal 2. In other words, that's saying as we go off to the left, we do have an asymptote at 2. But to the right, we go down to negative infinity. So I'm not sure what would be the correct choice, A, B, C, D, or E. But we know that 1 and 2 are correct, 3 is not. Another pretty straightforward one here. As I look at this one, I notice that it's a rational expression, which means that we have three options. We're either going to divide, we're going to do a substitution, or split it up. Well, since the power is bigger here on the bottom than the top, then we're going to do a substitution. I also noticed that the derivative of the bottom is very close to the function on top. So if I say u equals x squared plus 1, then du is going to be 2x dx. So far I have the x dx, but I need a 2 in there, so I'm going to throw in a 2. Which means I need to balance out here with 1/2, because 2 over 2 is really 1. I didn't change anything, but now I have the pieces that I need to substitute. So that means I'm going to have 1/2 times the integral, and we're going to go from one boundary to another, but we don't know what those boundaries are because they're changing. These are in terms of x, these are in terms of u. We have du over u, which is going to be 1/2 times natural log of u. Well, natural log of u is really natural log of x squared plus 1. So we're doing 1/2 natural log of x squared plus 1 evaluated from 1 to 3. If we plug in 3, then we're going to have 1/2 natural log of 3 squared is 9 plus 1 is 10 minus natural log of 1 squared is 1 plus 1 is 2. Notice that none of these have two terms, so that means that we're going to have to somehow compress this into one term. And we know that the natural log of a minus natural log of b is going to be natural log of a over b. So we're going to change this. This now becomes 1/2 natural log of 10 over 2, which is 5. The answer would be D. One other possible way you guys might see this is this 1/2 could become a power, which means that's the same as saying natural log of 5 to the 1/2 power or square rooted. So we've got to be aware of how those terms all kind of get manipulated. For this one, we're kind of going the opposite direction. We're taking the derivative of something with a natural log, but we still need to understand that u substitution relationship. Let's start with what u would be. Well, if we're taking the natural log of u and we're taking the derivative with respect to x as we are here, that's going to become u prime over u, or du over u, however you want to say it. So I need to figure out what u equals. Well, this would probably be easier if I split this up into two separate terms. So first, let's think of natural log of 1 over x squared plus 1 is equal to natural log of 1 minus natural log of x squared plus 1. If I take that a little bit further, I notice that natural log of 1 is really equal to 0. So this is just negative natural log of x squared plus 1. So I'm going to take the derivative of that. dx of natural log x squared plus 1. And this is a negative. So u then is that piece inside, which is x squared plus 1. Then u prime, or the derivative of that function, is just 2x. So the derivative of this is going to be 2x with a negative over x squared plus 1. Where did this negative come from? From right there and here. So it's negative 2x over x squared plus 1. How am I getting plus? Oh, because I don't even see that. You guys are probably yelling at the screen, Mr. Butler, why'd you make it a plus? It's a minus. So we got x squared minus 1, x squared minus 1, x squared minus 1, x squared minus 1. X squared minus 1. Awesome. So the answer is B, by the way.